You invited the wrong guy. So
now you start
joking.
Yes. Okay, so welcome back. Everyone, hope you had a good break. Did anyone try the notebooks and has like a cool transformation they've learned that they want to share a screenshot with us? If so, I think it's really easy these days to just take a screenshot, put it in the.
Did you do that? Wuchen didn't do that.
Wuchen didn't do it. That is a big surprise. Okay, anyway, if something comes up later, I will accept submissions through the entirety of the course, okay, or even after.
I think probably, Lars, people are just recharging battery quickly.
That is also fine.
And to be ready for the next discussion.
Okay, I will take that gladly as well. And as I said, now I think we have kind of laid the foundations a bit, so we can probably move a bit faster through the lecture and have more time to talk about other things. But I hope like so far the pace has been okay for you guys. Okay, so let's talk about the next ballpark of methods. So we've seen normalizing flows, continuous normalizing flows. To me, they are the easiest methods you can find in generative modeling. If they work, I would go for them any given day. It may seem boring, but at least it's relatively simple to get them to work. And when you start looking into the codes, you will see that it's not the end of the world to deal with. It's not this messy machine learning zoo that you are entering. It's still, things make sense still. Let's tackle one of their assumptions though and overcome them, namely that I want to tackle the case where Q, which is the dimensionality of the latent space, is different from N. And the motivation here should be the MNIST example that we talked about, where the intrinsic dimensionality we don't know, but it's way, way lower than the number of pixels in an image. Because that is an arbitrary number. You can even rediscretize the image and not generate new information necessarily by doing that or removing them. So the common case is that think about Q being way, way less. In our case, we want to go from 2 dimensions to 700 something. So that's a huge bridge we need to build here. Okay, we cannot use the continuous normalizing flow setup anymore, which is a pity. But you know that this may not exist. And also this, if you go into OKL divergences and you know something about those, they may not even exist. So maybe singular and all sorts of different things can happen here. So we need to find now a different way to define a loss function, because without a loss function, we cannot learn the weights of the generator. So how do we want to go about that? So here's a naive computation. So, I mean, I still like maximum likelihood training. That is a very natural idea, and that is very robust and straightforward to carry out if you can estimate the likelihood efficiently. So let's look at the likelihood after applying Bayes' rule. So you have a term here that is a joint distribution, or the joint likelihood of X and Z. And you have let me call this a posterior distribution. So that is kind of how likely is Z given for a given X. Okay. The first term here, this is a joint distribution. I can actually expand it by using the chain rule. So I can write this as PZ of Z. That is a nice guy. Let's just think about evaluating a Gaussian density. And then this term here is how likely is X given Z? Again, here I want to give my standard example where this is like X minus G of Z norm square. Okay. That you would make a few assumptions here on your distribution X, namely that it's kind of sampled from a Gaussian, and that's the appropriate likelihood then to compare generated samples and given samples. And here they're really corresponding to one another, because it's why you have this conditional distribution. So I hope you would agree that that this term here, so the joint density, is not so much to worry about. We could deal with that quite well. The harder part is the denominator here. because that one is a posterior. So I need sort of, let's think about this more from an inverse problem perspective. So you give me a sample X, and I need to tell you where it ends up in the latent space. Previously, it was a simple operation for us because we could just compute the inverse of the generator, and that would tell us exactly where we would end up. So not even a need to put a probability around it. The reason I put a probability around this whole thing is not necessarily because I always like to be in a Bayesian framework or to be in a statistical framework. Actually, probably for most of my life, I've tried to avoid this, sort of fancy statistical thinking, and I only use it when it really is needed. Here, I do think it's needed because you can very likely have the case that two different parts from, so G, at the end of the day, is a neural network. It's a completely nonlinear animal. So I think we should prepare for the case that two different Z's will be mapped to the same X, so you are not injective. In that case, I cannot define an inverse, doesn't exist, but I can always define a posterior distribution, because that could just be a bimodal distribution. There could be some noise to it, could be point measured, okay, but fine. But I want to prepare for this with a notation of using probabilities here. That makes sense. But anyway, this is hard. This is intractable. And just to point this out, so I cannot really maximize this directly because this part is intractable. Okay, so lecture finished. Not really, okay? So let's not give up so easily. Let's talk about a very straightforward idea. Since we are now machine learners, since at least for more than an hour, since you've listened to me, how about we create a new neural network that is basically replacing this guy? Great idea, right? Very original. So let's do this. So the posterior, the actual posterior is intractable. So let's approximate it. So here's my new network. I call it E, because it is kind of related to an encoder. We can talk about the relation a little bit more in a second. And I have to tell you two things. So first of all, there are new weights. I'm going to call them psi, and same rules as before. Psi is my joker that can mean anything and nothing. All the weights that you have in this network, which you have to create with layers, nonlinearities, convolutions, no convolutions, completely swept under the rug now. It's explicitly written down in the code if you want to actually know what's going on. So the psi here is definitely in there. And then X will be treated as the input to the network. So I give you X, and now I need to create this probability distribution, which still is not the standard way machine learners think about neural networks, because you give a fixed vector in and get a fixed vector out.
But now you do a density estimation.
Yes. Okay, so in VAEs, yes, we will use the notion of maximum likelihood and densities. So we kind of we will completely lose that in the GAN phase. So I'm preparing us for becoming more smoother. But yeah, sure. I mean, here I'm using probabilities, likelihood, there's a relation to KL and so on. Basically, I'm trying to carry over as much as I can from the normalizing flow now to this new reality that the dimensionality is different. Watch out for the next slide or so, where we actually tell you a little bit more what we can still say about this method that is coming out of this rather simple idea. Okay, so this E, remember, neural network, fixed number of inputs, n in this case, and some number of outputs. I'm going to use those to parameterize a distribution. So in my case, because it's Friday afternoon and I want an easy life, I'm making a really simple assumption here that is for sure not true in your data set, namely that this posterior here is going to be a Gaussian, so basically we are learning, I'm trying to indicate here with a notation that we are learning the mean of the Gaussian, and it's depending on X, and we are learning the covariance, which I will assume is diagonal even, okay? So it's a really limited type of model. You can easily, give me a hard time that this will not be a good model, because the generator, again, is a neural network, will be nonlinear. How likely do you think it would be that the posterior is Gaussian? And not very likely.
No.
But that's a going assumption that is out there. And actually, also, you can think about improving this through the mechanics that we've talked about in the previous part of the course. So there's an interesting direction here where you could think about using these flows to considerably increase the flexibility.
So what if you consider, is that biting its tail then? You consider the problem of being able to sample from this posterior distribution.
Yes.
And then approximate that by an empirical mean. Empirically. But that would probably I mean, lead in the next level to the same problem again and again and again.
No, I think you run, I mean, this, without too much thinking about this, probably you run into circles, namely that you need to sort of solve an inverse problem with your generator, which is what you would try to avoid here, actually. Right. Okay, so let me please remain really skeptical about this approach. Let me just show you how far we can push this with this rather naive idea. Okay, yeah, so again, the approximate posterior is sort of similar to an encoder, just in the sense that it gets you from the data space to the latent space, which is an encoder, you go from big dimension to small dimension and then back. But of course, here you have to think about this as the distribution, so you don't get a point valued thing. Okay, but that's just maybe fancy words for you. It is very similar. That's why I use E to denote it. Okay, so let's go on and take a look why this idea may not be as bad as it seems. So there's a little bit of analysis we can actually do. And that is now the training. So if I replace this intractable quantity with the encoder, and rather than minimizing over theta, I'm minimizing over psi and theta. I'm interested, what are the properties of this problem? And of course, I miss a minus sign here. That is not supposed to get out. Oh, God. Okay, sorry about that. So now what happens if we did this? Then here's a computation to show you why this would be meaningful. And I want to go through this. So if I have the log likelihood of the sample, I'm not changing anything if I put an expected value around it with respect to Z that does not really appear before. It's just a trick that will make sense in a little bit. But then I can massage this term a bit, so I can make this equal to the ratio. That's what we have derived previously with the Bayes law. Now I can, add a smart one here. I have an encoder here, an encoder there. Doesn't change anything. And I can split this up with the rules of the logarithm. Okay. Nice. Hopefully not so quick, not too quick, but trust me on this short derivation. So you can write the log likelihood equal to this term. And I now want you to look at the second term in particular. So the second term, I mean, of course, I could break this into two expected values. I just didn't have enough space on the slides. We could make this stop here, and then here put another expectation around. And that expectation would be with respect to the distribution given by the encoder. Right. So now if you look at this, then this is a KL term, no? Because you sample from the encoder, and you have the ratio, or the log of the ratio between the encoder and the posterior. So that is one property of the KL version that we all remember, is that it's not negative. That's the only thing you need here, which means that, so this term here is going to be non-negative. And if I dropped it, which the proposal that I have up here actually would do. So if I dropped this term, then I would basically have a lower bound on the likelihood. Okay. And the nice thing now about having the lower bound or the lower bound on the likelihood. Sorry, actually, it's important. One thing I think I'm switching between minimization and maximization all the time. So here, one important note is, so we have the log likelihood, and here I would actually want to maximize it.
Yeah. Maximum.
Right. So probably this was not a bug, but a feature, but I have to go through, there was some inconsistency. So we want to maximize this. Let's figure this out together. I want to maximize this guy, and this is intractable, but I can maximize this lower bound. In principle, it's a meaningless thing, right? Because we all can imagine a case where maximizing the lower bound of a function will be different from maximizing a function we're interested in. However, when I do this, then look the difference. I actually know something about the difference between the lower bound and the actual value, and that is kind of given by the KL between the approximate and the true posterior. So if I manage to learn the true posterior,
this would be 0.
This would be 0. It would go away, and I would actually do likelihood maximization. Right, makes sense. So it's kind of a bound that becomes sort of tighter, and of course, maximizing this term also in the same time minimizes the KL here, right? Because I'm pushing the. I mean, this is a constant log p theta with respect to, say, psi. With respect to psi is the constant. So if I maximize this term with respect to psi, I am making the bound tighter and tighter. So I can, again, kind of, it's kind of maybe came across as a hacky way to tackle this problem, but I am actually minimizing this implicitly, even though I cannot compute it at any given time. So that is, I think, the idea why these variational autoencoders became really popular, because you can actually say something about the relation to maximum likelihood, which we saw in the previous part is actually a very well-meaning framework for us.
What bothers me about this is the underlying silent assumption that your network is rich enough to actually reach your guy.
Oh, yeah, and Wolfgang, that is really the unsettling thing that I want to be brutally honest about, because with our way of constructing the encoder, you talk about already the expressiveness of the network.
Yeah. We
don't even have to talk about that, because the true posterior won't be Gaussian. So whatever you do inside is not going to be right. And but here one thing you can see here is that you explicitly sort of still have a control over, so the error that you're making in the approximation will be reflected in your optimization. So with a better encoder, for example, I would expect that you can make this term smaller for any given theta, which simultaneously would make this one larger then. So it's still not flying completely blind. The better you will do, the smaller this term, and the better this term should be.
Right.
So that's prepare for the gun. It'll be way more messy, I can promise. So anyway, so that's kind of the justification for doing this replacement. So take the intractable guy, replace it with a neural network, and then, or with a distribution parameterized by a neural network, or more generally, don't limit yourself all the way to neural networks, a variational inference model. So anything that transforms a distribution or parameterizes a distribution can go in here. Okay, so that's called the elbow empirical lower bound training. Again, so sorry, there's just some overlay issues. Let's look at this, how you would actually do the training, because that's also one thing to note. So in the training, I mean, I have kind of, so that's basically rewriting what we had, not in a ratio, but using the logarithm rules. And hopefully having the right minus sign in front of this, namely here. So you sample data point. For every data point, you get an encoder distribution, and you sample from that, or you take an expectation with respect to this z, and then you compute this sort of KL-like term, where you have a difference between two different blocks. Okay, so you can reformulate this, of course, as a likelihood of x, and the prior, which is a latent distribution. That's just some gymnastics. But then you will use an SGD type argument, so a stochastic approximation of the problem in reality, by summing again over some batches of samples. And now I'm going to make another assumption that will for sure make Wolfgang uncomfortable, and probably everyone here, because I have two expected values to worry about. So the first one, I can easily do the same thing that I did before. I replaced it by this term here. The second one, I'm actually going to replace this by just one sample. So as a Monte Carlo with one sample. Oh. For every xi, I draw a zi. Of course, you have access to the codes in a little bit. You can use more if you like. But that is so what everyone is doing. I want to reflect kind of what everyone's doing. I'm not so invested in VAEs, and not by far not the most VAE expert. But that's what apparently is the rumor on the street, that that's a great idea. It isn't okay. So to give it just some justification. So whenever you use SGD, what you're worried about is to get a unbiased estimate of your gradient. And this is an unbiased estimate of the gradient. I mean, even doing SGD on one example from the training data would be unbiased. So it's okay. That's the reason to say it's okay. Of course, you will pay at some point, because the noise that you have is now sort of twice as much, because you have two sources of noise: one sampling the data, one sampling from the posterior. Okay, but anyway, that's what we'll do. Yeah, it can be very noisy. And then here's again this argument that if you minimize this loss function again with respect to psi for a fixed theta, then you actually improve the tightness of the elbow also. Okay. The one thing already to say is in this case, it's kind of the psi and the theta play a game together, actually, because they are both minimizing kind of the same problem, or working on the same problem, which will be, generally speaking, in my opinion, minimizing a function is much easier than finding a settle point. So we can pick up that discussion in a little bit. So that's also one reason to actually like these variational autoencoders. Okay. I can take it one step further to look into the problem a little bit more, namely by rewriting this part that we saw in the VAE. Because Wolfgang likes KL divergences. I can give him one more KL divergence in here. Because you have, in principle, so you sample from the encoder. So you can look at this last two terms here and think about this as a KL divergence between the, that's now really important to pay some attention, between the approximate posterior for a given x. So x is given around some part of the latent space. You have a Gaussian, and you penalize the KL divergence between that Gaussian and the whole latent distribution. It's a weird animal, because then you take an expectation also over the x on the outside. What this does tell us, though, is that you try, you can think about it this way, that you try to have the samples that you take, so basically the latent variables corresponding to your data points, you try to make them somewhat Gaussian. You don't want them to be anywhere far from the origin. You want to pull them, say, to the center and make sure. So this first term, by the way, is called the reconstruction loss. That's how well you can go back from z to x. You want that to be small, but you also don't want the reconstruction all over the place, scattered around. So if that makes sense to you, then you can immediately think about this whole problem as a regularization of the normal autoencoder. Because the normal autoencoder would basically only minimize the reconstruction loss. It wouldn't matter where the Z's are, how they look like, how the latent space would look like. It can be all over the place as long as you really get the best reconstruction possible. Now you add a little bit of regularity, and in this case you pick a KL divergence for some reason, but there could be other regularization terms that basically penalize how non-Gaussian your latent space looks. So I have a few ideas that are out in the literature about this. What's kind of an interesting discussion we can do in the break is there is, of course, an inverse problem. So this all has a really big smell of inverse problems. Actually, you can think about this one here, the approximate posterior. I mean, in a Bayesian inverse problem, once I have the posterior, I'm basically done. I've solved my problem. Now what you actually try to do here is the X is sort of the data in the inversion. You do an amortized inference. So you have the same side that kind of should give you all the posteriors for all the data set, for all the possible data. In the Bayesian framework, that's a really powerful thing again, to be able to do that. In a Bayesian framework, basically you are tied to using these type of loss functions, and this specific regularizer. Frequentists are a little bit more liberal in the sense that you could replace this by anything that penalizes non-Gaussianity. So if you think about the VAEs, you can design VAEs that way. The only thing you would lose is the lower bound interpretation. And you can decide on your own if this is important to you or not important to you. Because again, it's you maximize the lower bound, so how the meaningful of the bound depends on all these choices that we've talked about. So if I'm giving that up, but I get a much more effective generator, maybe I would buy that. Anyway, let's just putting out some ideas here also for you guys. Okay, so yeah, again, autoencoders typically have no regularization. So what this means is that the latent space, which I mean, take, say, your whole data set and sample a bunch of points from the respective posteriors or the approximate posteriors, and look how the point cloud looks like. For an autoencoder, you have no reason to believe that this would resemble a Gaussian. Here, also not so much, because you have two terms here. You have the likelihood and the regularity that are going to be traded off somehow. But at least you have some notion of regularization in here. And we'll look at an example now. Okay, so here's the example. And again, you can use the break to play with this example. I will show you one important thing when you do this, if you try to use this on Colab. And you should be able to achieve, again, with a two-dimensional latent space, you should be able to generate images that look like so on the right-hand side. And okay, who knows if this is now good or bad? It's not a terrible result. I mean, you can easily recognize the letters there. However, they're a little bit blurred. That's a bit disturbing in some sense. So you could easily tell which ones I created and which ones I didn't. But you can do this and train this in like maybe 5 to 10 minutes on your own, if you like, with not so much fancy things going on there. An interesting thing going back also to the discussion with Wolfgang is to see how the posteriors actually look like. So that's an example kind of I really wanted to create, and it took me a little bit of a while to figure this one out. But in this example, since we're in a 2D features latent space, we can actually plot many things that, in high dimensional problems and real data sets, not MNIST, or real complicated data sets get lost and you don't have at your disposal. So what I show you here, so that's a true image, probably a 2 or something like that. Then you can look at, so this top here actually is up to a constant, the true posterior. So I've gone through a few hoops to compute this guy, basically using Bayes' theorem and doing lots of sampling and so on. But I can actually compute for this generator, how would the actual posterior I'm trying to fit look like? And I hope you can see that this is not a Gaussian. So these are the contour lines of the density, or the log of the density. It's definitely not a Gaussian. There are multiple maximizers, in this case, multiple modes. But overall, so here's my approximation to it. And I'm denoting like this red dot is the same in both. No, I mean, I kind of get close to, I mean, they're not completely different. They're not the same, but for sure. I'm not going to argue about this, but they are also not completely different. And in some sense, also the minimization would sort of regularize the generator as well, because the generator has an incentive to not only fit the data, but also become Gaussian. This example, though, was picked in a way that I kind of show you the worst case behavior for my problem. So this is the one giving me the biggest reconstruction loss, because what I show you here on the right-hand side, so you, again, it's an autoencoder. So you take this image in the way the way it's actually solved the problem, you go to the latent space to this point here. And from this point, you use the generator to go back. But where you end up in this example is actually this image. And I don't need to have a vote here that this is not a great reconstruction. So if you give me, I mean, maybe it is if you give me $2 and I give you back $6, then you'll be happy. But not in all cases would you be happy with a conversion like that. Like in German high school, like if you give me, like we have grades from 1 through 6, and the lower the score, the better. Probably the students would not be happy if I use this generator to grade their assignments. Okay, so this is not a good example. However, if you pick so here you have the true posterior. So we could compute basically the map point of the true posterior. If we use that to reconstruct, you would at least, I mean, you would not get the same image back, but you would get closer, at least in our norm of things. Okay, but this is really the price that you're paying here, because I mean, your model is not, like you can look at it two ways. So the encoder is not rich enough to fit that particular generator, or the generator is not rich enough to transform the Gaussian variable to the data space.
It's okay. A general question.
Yes.
I mean, the discriminator in a GAN framework, generally, is it fair to say that the accuracy requirements on this one are actually not that important?
There's a reason to say so, but it's a very disturbing one. And again, we'll touch about that, well, where sometimes it pays off to not have a really good discriminator.
I will tell you one instance where this is the case. So I can reinterpret, say, finding a good training risk for pins. I can reinterpret that in a GAN framework.
Mm-hmm.
And,
sure.
And there the adversarial guy will in the end represent the reslift of a function.
Okay.
And whether I get that reslift, if I get that reslift just in relative accuracy, it's okay.
Mm-hmm.
So I want, but it's not clear to me whether this is actually a general rule. But in this case, I think this guy also regularizes.
Okay.
Sort of automatically.
Yeah, I mean, yeah,
the generator. Let's put this, the generator. But yeah. I'm not fully understanding this.
Yeah, I think probably empirically that is an observation that most people in generative adversarial networks would agree to, that there is this relation, but it's not as obvious as it is for VAE. So for VAE, I think the behavior sort of is quite predictable in the sense that you know where the source of error is. That's how well you can invert the generator.
Mm-hmm.
The better you can do there, it should translate to better generated images in our case. And the more poorly you're going to do this, you will see a price that you'll pay here in terms of bad reconstructions or non-realistic images.
I see.
Yeah, again, so here's the notebook you can run. I can show you a little bit one important trick when doing this. But what I'm really intrigued by also is to look at the structure of the latent space, because there's one, actually, LDAT, when we worked on this, was really pushing hard on getting a good visualization and a good handle of what's actually going on. And there's one really interesting part that is very different from a GAN, and that may explain why sometimes GANs perform better or worse, typically in some respects better than the VAEs. So if you think what you want to do, so you want to train a generator, right? How is the generator going to work after the training is done? You pick a sample from a Gaussian, you put it into the generator, and you want a nice image. Everything we know about deep neural networks is that you should train them exactly on the task. Ideally, you should train them on the test data. So you should train them really under the scenario of how you want to evaluate them. In a VAE, that is not what's happening, though, because where you sample in the training, so you sample an image from the training data, and then you sample a latent variable, but you don't sample it from the prior. You don't sample it from the normal Gaussian. You sample it from the approximate posteriors. So it becomes interesting to look at the latent space and how they are distributed. So in our case, I've shown like just the means of all the posteriors, and I've color coded them by the labels, because we have a labeled data set. We didn't use the labels so far, and of course we're also not using them in the training, but it's kind of interesting to look at. So this class here would be the same digit, and they kind of go together in the latent space, which I find kind of interesting to look at, because it was not trained as a classifier, but in some sense, you magically they end up in the same space. But what's more important is that those ones here overall, they're not really Gaussian. I mean, they are centered at around 0, I would say, if I took the mean here, and the covariance matrix may be somewhat isotropic, but it's not a Gaussian. And if you look at, you draw many samples from all these guys, then this is going to be the density you would get. So that is the density you're using in training. So you're training more on those points, but you're missing part of the space that is actually supposed to be used in the generation. So that is somewhat disturbing in some sense, right? Because you shouldn't expect them to see a greater performance. Here's the surprising thing from my example, which in general will not hold true. So one thing I wanted to look at is, so I have these parts in the latent space that the prior will very likely pick, but the posteriors are very likely to miss. So think about this area here in the very middle. That is with very high likelihood going to be part of the image generation later on. So I've done an experiment where I kind of put a few points in here and look at the images. I didn't see an obvious pattern, but the images didn't look horribly, but they looked also not great. But the overall images also, like I would say, looked a bit too smooth for my taste. But it's not like there are cat and dog images in those spaces. So it's a little bit of both mentioned generalization, tiny little bit we can see for this particular example, but it's the really key problem, I think, for the VAEs, that you don't really train on the task, because you're not training the generator on the inputs that it will be given later on. Okay, cool. So that's kind of a quick summary for that part. Again, that's the problem we are tackling. So the generator we want to train, and this is kind of the main direction here, where we will have an approximate posterior that we are going to learn, which is nice in the sense that there is a notion of correspondence between the latent space and the data space. And of course, having a correspondence means that we can look, for example, at the reconstruction loss of the generator. of the encoder and the generator. If we have no correspondence, we really have to look at the training loss in a distributional, in comparing distributions. And so VAEs at least circumvent that problem somehow, because there is a notion of correspondences. Yeah, you can see this as a relation to autoencoders. I think is quite interesting to have, because then you can think about regularizing an autoencoder to get sort of this Gaussianity in the feature space. But the disturbing part really is that so that you train the generator using samples from the approximate posteriors, but not from the latent distribution. And that is, yeah, that, and also, as we discussed, the difficulty of measuring the, or getting the lower bound really tight by having a powerful posterior model here. It's probably the, yeah, kind of a limitation of these VAEs. On the other hand, though, it's the nice thing is it's a minimization problem, period. So in terms of how much energy you will use to find hyperparameters, you should expect to do a little bit worse on what's coming next. So with that, how about I stop now? And we are back to this rhythm of having, what is it, 20-minute break to 4:15. You can use this any way you like. Maybe Peter wants to stop recording so we can have casual discussions here. And you can also look at the notebook. And I want to show you the notebook real quick. I think, where do I have this? In here, to make one comment about it. That's how we go. So now you should see my my browser. And if you go here, so of course I started this very early for you. So if you go to this VAE notebook, which I encourage you to do, since we're looking at convolutional neural networks, you don't get anywhere without the GPU. And if you didn't know, you can look at the runtime and change the runtime type so that you can use a GPU here. By default, it will be put to none. So that will be all computations on the CPU, but you definitely want for this one to use a GPU. And then you save it, and then you can hit run all, and it should just go through and give you some results. It may take a little bit to download the data set. That's something I've realized is becoming quite slow, but that's kind of the results you would expect. So the right-hand side are some samples, and you can do other funny things here, and you can take it really apart if you like. And again, the optimization is interesting. You can play with this, but it's overall less involved than what we'll talk about in the next phase. So how about taking break until 4:15 and then reconvening? Yeah, and I'll be around here.
Good. Thank you.
Sure.
Yeah, thank you. And I stop recording, okay?
Yeah, fine.